No? I'll call it. I didn't know I had an esports team.
Easy ass shit.
It's always having a day where you can come over and do interviews. They show you around their facilities. That's just the day before the hackathon, which I think is on the 23rd, 24th.
I don't even remember.
Yeah.
That was your first question. So I walked in with my fucking my coffee that's in it's 5 o'clock somewhere. What is it? By the way. And then just got way more relaxed than what do you do for fun.
All right, so we're gonna start. Yeah, I think you guys know why you're here. We wanted to start a rocket engine club on campus.
Hell yeah.
I love the enthusiasm. Obviously, we're not gonna fly this because that would be a missile. So we're gonna do static testing on the ground, but everything else will be the same as the rocket engine. So this presentation, we're gonna go over some of the physics, like I said, subsystems, project management. We'll show you some clips of some of the things that like kind of other students from other schools have made, and so you can kind of have an idea of where we're going. Our general idea is that we're going to build a smaller scale test, or smaller scale first, and then go up from there once we make sure that we have everything right. We're not blowing each other up. So, Matt, we're getting started, I guess.
Yep. All right. Thank you for coming. Again, my name is Makar. I don't know everyone, but I know a lot of people. So thank you everyone for coming. This is a club that I've kind of wanted to do for a long time, and now that we are having our first meeting and there's a lot of people here, I'm actually quite nervous. But you know, let's do our best. The purpose of this club is to develop rocket propulsion systems and test infrastructure to advance members' personal competency in the design of complex physical systems and to gain a deeper understanding of the rockets themselves.
That's a run-on sentence, but it really
yeah. Let me show you what a rocket engine test or a small scale amateur rocket actually looks like, because so we're on the same page. So yeah, this is what I mean by liquid rocket engine and test bed.
And we have a couple other ones.
Yeah, we have other ones.
From like USC. So there's clubs at like USC, Purdue, MIT. A lot of schools actually have a surprising liquid propulsion group. So that also means that there's a lot of resources for us to go off of. So this isn't like we're not just stumbling into this. And I think, so I'm going to show you, this is USC's rocket engine, it's called Hydra. This is their first test. And I'm going to show you, this is from 2017, they have a test from 2018, 2019 that's a little different, and it's better, it's more polished. And I thought it was important to show you guys this so, to stress the importance that it's, like, we're not going to get this right the first time. It's going to be tough. And we're going to fuck up along the way. It's just how it is. But if you, like, through these videos, you can see that you can improve. And that goes to the importance of our control systems and making sure that we're analyzing what we're doing so we get good feedback, so we can constantly improve and keep moving forward instead of kind of getting stuck and then, you know, getting upset and shit. So this is USC's first test. Oh, this one just happened.
3, 2, 1, 9.
Just presenting. Yeah.
So that was there. I'm gonna go to the fourth one so you guys can see. So that one was like it fires, everything's great, but you can see a difference. you can kind of really see how smooth it is, and that's kind of like you'll see videos of really rough ones where it's just kind of screeching and it doesn't sound very nice, doesn't really look that great. But those are like little parts that you can improve upon, and that's kind of what we're working towards. Oh, we missed that.
Yeah. No, it's okay. We'll show you.
All right.
But yeah. So yeah, what do you guys think? This is what I mean when I say liquid rocket engine development club and test stand. It's not necessarily like a vehicle. It's not a rocket that you make and then you fly, because you have to really nail the propulsion first if you do want to fly anything anyway. And to me, I think that the engineering and the physics that goes into the engine itself is pretty hardcore anyway, and that's where my personal passion lies. What do you guys think?
When do we start?
I feel. And yeah, Jürgen was talking about how in a complex system like this, you are likely to experience failures. And we're going to talk more about how the system is going to be made in a redundant fashion and how the procedures are going to be done to mitigate risk. But even hazardous complex systems like this can be operated and tested safely, and that is something that we're going to try to exemplify. Why this project is important to me personally is because, well, space is kind of taking off, pun intended, I guess. Ever since SpaceX came around, commercial launch and price to orbit has been decreasing. It seems that we're kind of in this precipice of a new space age, and there's going to be lots and lots and lots of things to do in space in the coming years and decades. The propulsion element itself kind of enables everything that goes on. In order to get to space, you first have to get on the rocket. And developing better rockets, better launch vehicles, is kind of what enables all the advancements in space from here on out. It's kind of like this most very leveraged effect on humanity that you can have if you know how to make rocket engines. So that's kind of my personal reason. But from just a general reason, even if you're not going to go into aerospace in the end, or maybe you don't want to be a propulsion engineer, I hope that this organization can be a very interdisciplinary learning environment where you are working on a complex project that spans a long time, has delivery deadlines, has project requirements, and that you can learn a lot of things from other talented people, and you can specialize in something, and then you can own a part of the system and then develop it over time and gain real engineering experience like this. And in my experience getting internships and in the industry, that's what the employers are really looking for anyway, because project experience exemplifies or kind of shows to them that you're skilled and you can apply it. So it's kind of, even on just that level for the resume, I think this could be a very good project.
And that you work well with others, because I had an internship at Collins last summer, and I talked to my hiring manager about really about like what makes a strong applicant, and they were telling me that they want someone that can admit that they don't know something. They don't want someone that knows everything. They want someone that's admitting to like that they don't know something, but that they're willing to learn it, that they're willing to ask for help, and that they can get along with others. Because I think we all know like those really, really bright kids that just don't they don't communicate well with others, they don't work well with others, they want to do everything by themselves, they want to do it their way, and that's not how you accomplish a goal like that we're trying to set out to do, or that other clubs like Formula have set out to do. So I think that's really the most important part about this, is learning how to work with the team, work with each other.
Yeah. Any questions, comments? Okay, so then I want to give you guys a quick, before we go into the project itself and how it's going to be managed and how we're going to achieve our goals and what our goals are and deadlines, I want to give you a quick physics overview and subsystem, and tell you what the subsystems are that go into making a rocket engine work, to maybe see if you guys have something that you want to specialize in. So top down, the rocket engine, all the rocket engine does is converts stored chemical energy into kinetic energy of the gases. This is accomplished by having an oxidizer and a fuel, usually liquid oxygen and either like kerosene called RB1 or liquid methane. And then when you burn them, you release a lot of that internal energy, and you can convert that internal energy into velocity of the gas. And as that gas exits the nozzle at really high velocity, it imparts kinetic energy back on the engine and you have thrust. Over here, we'll be talking more about the physics in depth on like later deep dive meetings. But this is basically a velocity profile of how flow works inside of a rocket nozzle. The rocket nozzle is called a converging diverging nozzle, where the converging section is in the subsonic flow and the diverging section is in supersonic flow. So in that way, you can convert internal temperature and pressure energy into velocity of the gas. That's basically the main thing. And everything else about the rocket is enabling that to happen, essentially. Because you need to burn a lot of the stuff and you need to throw it out. Okay, well, how do you enable that? And that's where the different subsystems come in. So, next slide. If you want to make a rocket engine, and not even one that flies in a rocket, but just one that functions on the ground, it's pretty much the same thing. And here I have a picture of the Falcon 9 and the Merlin 1D engine for reference, but this will be systems that we're integrating into our test stand. You essentially need a place to store the propellants. You need a way to deliver those propellants to the rocket engine. You need a way to pressurize them, and then to burn them, and contain that, essentially, flame, and cool the chamber. So this is kind of how it goes. You got the tank structure here, propellant feed lines going to the engines. The engine has some sort of way to pressurize the engine. In this case, it's a gas generator, but we'll talk about that later. And then it cools itself by passing fuel through the chamber and then injecting the fuel in here and burning it. So it's kind of like, this is where the rocket part happens, and this is, you can think of this as supporting infrastructure almost. And that's the things that is kind of behind the scenes for the rockets. And that leads me to the subsystems. We're going to break it up into subsystems like this. The first subsystem is going to be called propellant storage and plumbing. The propellant storage and plumbing essentially is the pressure vessels that contain the fuel that then feed the fuel into the rocket engines. What we're going to be making is called a pressure-fed rocket, which means that you have a pressure vessel that has high-pressure helium in it, and you use that helium to essentially pressurize the fuel that's in the tanks, and then push that fuel at high pressure into the chamber. Because a rocket's efficiency increases with chamber pressure. That's one of the things we'll talk about later. It seems pretty simple, but it actually has a lot of hardware that goes into it, because inside of the plumbing, and this is kind of called the plumbing system, and this is usually called the tank structure. But I guess in our case, we're not supporting a rocket really, or like a launch vehicle. We're just going to call them propellant storage. The propellant storage, it's not just two tanks and like a hose. It has to have a lot of data acquisition, like transducers. Cryogenic valves are hard to make because they shrink and expand once they are at different states. Like when you put, for example, cryogenic oxygen into a valve, the inside of the valve is going to shrink, and that's going to mess with your tolerance at the like if you were using a ball, for example, a ball valve. It's stuff like that. It also has like insulation over here. This is Copenhagen Suburbal's propellant storage system. They got like their liquid oxygen, their fuel, and then they push helium in at the top, and then the pressurized fuel comes out of the bottom and goes through their engine. That's going to be one of the subsystems. Another subsystem is going to be the injector, and this is where the fuel comes from the propellant feed lines and then enters the rocket engine. There's different kinds of injectors, but essentially the point of the injector is to spray the propellants and mix them evenly and make sure that the flame inside of the chamber is burning evenly, essentially. So there's no hot spots on one side or the other, and that a high mass flow rate can be supported. There's different kinds, like there's a pintle injector, and we'll talk more about these later. Pintle injectors, for example, that kind of spray the fuel and the oxidizer from two concentric tubes. You got coaxial swirl injectors that have like a plate where liquid oxygen enters and the fuel enters, and stuff like that. It seems simple, but this is going to be probably the hardest part to manufacture because the tolerances have to be super tight, and it has to support a lot of load. Because it's one side is on the cold end of the propellants and the other side is inside of the chamber. The chamber temperature is something like 3,000 Kelvin, so it's no joke. Moving on to the chamber itself, the main thing about the chamber is the way it has to be manufactured. The point of it is to be the place where the combustion happens. it has to have the converging and diverging nozzle sections, which means that it has to be shaped correctly to support the different types of the flow, as I talked about, and it has to be cooled. So because the inside of the chamber is at like 3,000 Kelvin and the outside is ambient air, you have a super high heat flux through the chamber walls. What you can do, one of the things that you can do is you can just blast water on it for just an engine test. The other thing you can do is actually cool it with fuel. So what you do is you put fuel at the bottom of the chamber and it rises through a cooling jacket and then goes into the engine. And that's called regenerative cooling. That might be an option that we take with the first engine, maybe not. And then the third subsystem, or it was kind of two more. You got the electronics and then you got the controls. So the electronics is essentially what makes everything run. The rocket is the chamber itself and it burns, but it also has valves that have to open and close, and then it also has to have all this data that's collected on it. How much thrust is it generating? What's the chamber pressure like? What's the pressure like at all the different points in the pipe? What's the temperature like? Is anything freezing over? Am I boiling off my propellants too fast? Am I creating high pressure conditions inside of my pressure vessels, making it dangerous? All of that has to be measured by the electronics and instrumentation. So I got like a thermocouple pressure gauge, a Raspberry Pi. We're gonna run redundant computing systems, and essentially we're gonna have two controllers that can measure everything about the rocket and know what to do based on what they're measuring. So yeah, that's the electronics, and that leads into the control, which is the next subsystem. This is the programming heavy one. Essentially, the purpose of the control system is to have control authority over the system and to ensure safe operation. So it needs to know how to light the engine, in what order it should open all the valves, what each state of the rocket has to be, when is it safe to approach, like how do you make it safe to approach, what does the control system have to do? And the test stand is going to be like far away from us, so when we're testing it, we're over here, so we have radio communication to it, and this is what the programming that runs the show. And this leads me to the test stand, which is the other subsystem, which is like the box where you put everything. The test stand, oh, there's no test stand. Okay, well the test stand just kind of puts everything together. It supports the tank structures and the rocket, has the power supply, and we're also going to add a fire suppression and acoustic dampening systems. So you can spray water on it, and if everything catches on fire. But yeah, I know I'm talking really fast. I don't really know how to tie this together well, but this is kind of what goes into making a rocket engine as I see it right now. Do you guys have any questions?
Probably a lot.
Yeah, what's up?
What materials are you planning on?
Gotcha. So the material selection depends on the constraints. So in order to select the materials, you first need to know what the operating environments are. I'm favoring steel right now.
Yeah, because you had about 3,000.
Yeah,
right?
that's right. So
you warping is going to be a bitch.
that's right. So you got yielding of the material due to thermal stress. You got issues. You can have the material straight up melting. You can try to actively cool it. So you can have materials that have a lower melting point, but you can try to actively cool them and calculate how much like water or fuel you have to put over it to cool it in that time. There's other exotics that you can use.
Can you
like
coat it with something?
You can coat it with stuff. Yeah. So there's different ways to cool. Okay. So you can coat it with something called a phenolic ablator, which is a type of polymer that will evaporate and create a boundary layer next on the inside of the thing. That's how they made early heat shields. It kind of like evaporates and then makes a little shield to insulate the chamber walls.
Okay.
You can also make it out of exotic nickel alloys like Inconel or just higher melting stuff. But that is something in the project hierarchy. We're going to define what our project requirements are first, and then we're going to make physics models, and then we're going to go into the engineering parameters selection, like materials and what needs to be done. So that's kind of that. What do you think? Okay.
I mean, it's just a lot to think about.
Yes, sorry.
Yeah, so like, that's kind of like the next thing that we're gonna talk about. When I first started talking to Makar about this, he knew so much. I was like, I think
Fake
rockets are
news.
cool. That's a damn lie. I think everyone knows that. But he knew so much about rocket theory, like right as because he talked to me. He's like, "Oh, you're interested in rockets?" I was like, "Yeah, like I think it's cool." I watched a couple stupid videos on YouTube about it, and so he started talking about the theory. He started using these like 5-syllable words, and I was just really like caught off guard. I was like, "Dude, I don't know what you're saying right now." But he said, you know, if you're interested in like making something, I'd be like, I want to help out. Obviously, I didn't know shit, so I talked to him a lot about theory, but he pointed me in the right direction for resources to learn and stuff. And this kind of leads into the next thing that we're going to talk about, and this is the imposter syndrome. This is something that I think almost every engineer, maybe every person in their major really has, and it's kind of like, I know I've had it for sure. It's like you feel like almost like a fraudulent engineer because you've taken all these courses, you know all this stuff, but you haven't really applied it, and you can kind of get into this idea of like sense of like self-doubt of like what your abilities are, how far you can push yourself, how much you can contribute, and you kind of put limits on yourself. Like I'm sure even just listening to him talk about the subsystems, I was getting like flustered and stuff, and I've already like seen most of this stuff. So we'll dive into like once you guys figure out something that you want to work on, like a system that you want to be a part of, then we're happy to point you in the right direction to learn some of this stuff. This isn't gonna be something that you're gonna get really quickly, and it's gonna take time. It's gonna take like motivation on your guys' part. That's why you're here. You're interested in this. This is what like brought you here in the first place. So for now, really, all we're gonna ask you guys to do is just go and like watch some videos. We have a bunch of resources up on a OneNote, on a drive that we'll share with you guys. If you guys have questions, obviously text just Makar. Don't text me. No, I'm just kidding. But text Makar. Text me. We'll point you in the right direction. We can help you. The most important thing is that you guys understand that we're learning too, and we're interested. Like, if you guys have any ideas, if you guys find something you think is cool, it doesn't have to be applicable, but something that you want to share, do it, dude. Like, I'm all for it. I think this is really cool to me. This is what I want to do. So, yeah, I think that's the best part about these kinds of clubs is like the culture that is created. It's kind of like an experience that you go through and you share this education with each other, and we kind of build each other up. And the idea is that that's like what the team does. So the imposter syndrome is like a big part of that. And I know this is a lot to take in right now, but we'll be breaking it down in simpler terms and like smaller sections, so you guys can tackle it with more confidence and not sit there like, what the fuck is going on? So, anything else to say?
Basically, I want to build a rocket engine, and it's hard, but I want you to build it with me, because everything difficult that was ever done by humans was done by humans who didn't know how to go about doing the difficult thing. But they started, and they figured it out as they went. I see rocket engines as this really cool confluence of a lot of engineering disciplines that excite me and make me like that I'm really passionate about. And you guys are very smart engineers. I would very much appreciate it if you guys wanted to try to undertake this endeavor.
Help us help you, because like we said, we don't know everything, and we're still learning. So the most important thing is that you guys know this is not going to be something overnight. This is like, it's kind of just like if you go hit the gym, or if you're trying to lift weights and get swole or something. It's like working out your brain like 30 minutes to an hour every day. By the time June comes around, you guys are going to know so much. Shut up. You guys are going to know so much. You're going to like look back for like to now and be like, wow, I actually like kind of understand those 5 or 6 syllable words that Makar was throwing at me. Yes, that was kind of like the most important part. Yeah, what's up?
All right, let's take a small break and talk. Yeah.
My bad. Because you're not actually flying it, it's like, I don't know, from the videos, like connected to a wall or something.
Yeah.
Is the main power source electricity?
So the main power source for what specifically? For the control systems or for the rocket?
Well, I'm going to say control system.
Mm-hmm.
Because a control system will control the rockets.
Yes. So that, since it's an isolated system, the test stand has to make its own power essentially. It can be probably achieved with batteries, but we might have to see other options. The rocket engine powers itself kind of using pressure. So you have a pressure chamber, or sorry, a pressure vessel, and that's what's powering the rocket kind of. But
So
the
we're
test.
gonna have valves moving
Yes.
based off of pressure?
Well, they can be, so yes, they could be electric valves or they could be hydraulic valves.
Hydraulic.
We don't know yet.
Okay.
That's something that has to be decided. But yeah, you have to think about that kind of stuff, yeah.
And just as like a thing, do you know where to buy the gases?
The gases is not the hard part. You can buy them at air gas. The hardest part is going to be the cryogenic components. So for example, the cryo valves and the KF, the standard like feed lines that can support cryogenic flow and really high mass flow rates. But this can be purchased online, so it's no restricted shit.
Okay.
It can be done.
Also, I think, I'm sure a lot of you guys have questions. I don't know if you guys would be interested in this. I just thought about this right now, but would you guys be interested in like, I don't know, like a channel? Like if we make a Slack, and we have like a Slack channel for like just questions, just so you can like write it down and just put it up there. So one of us, if someone knows it or someone has come across it, because that's kind of how we're going to be able to help each other. And those are really, really good questions that he's asking, and I encourage you guys to think about those things too. Don't be afraid to ask.
They're design questions. This
Yeah.
is what has to be solved.
These are really important questions.
Yeah.
So just if you guys have a question, just write it down somewhere. Like ask us, text it to us, email it to us, because this is how we're going to make sure that we're building the best thing we can.
Yeah, what's up?
For the Raspberry Pi, what
Yeah.
programming language are you guys
Rust.
using? Rust.
Yeah, Rust. What's up?
I didn't wanna-
Rust because it writes like C and it's more robust and it has better memory management essentially, and yeah, it's gonna run on two redundant pies. So the pies we're gonna make a system that allows them to communicate with one another, and one of them to monitor the other one's behavior and take over if one of them fails. It's gonna be pretty cool. So the guy who I'm talking to, who's part of this club, but he couldn't make it today. His name's Joseph. He goes to Davis, and he started work on the system. If you want to work on the controls programming, I can. Yeah.
So next slide.
What?
Project management.
Let's take.
Oh, yeah, you guys
Let's talk.
have a question?
I wanna. Yeah.
I had a question on the Raspberry, but I was wondering why you chose that, because there's no analog to digital converter.
You could add you could add ADCs. You could also use other embedded. So I said Raspberry Pi. It essentially has to be an embedded system that can do microcontrolling and has an ADC and can control all of our analog systems. So maybe Raspberry Pi isn't the best option. I don't know. That's something that has to be decided. So yeah, sure. Yeah, but that's a good point. What do you guys think?
Well, what is the timeline you're kind of looking at?
That's next. Yeah.
Wait.
So project. Let's go back to the project management one. Yeah. So project management. We're gonna run it as a project would be run inside of a company essentially. So there's going to be project requirements that we're going to develop over the next week probably, that are essentially the project requirements outline everything that the system has to achieve. So for example, one of them can be like, all valves have redundant state measurement circuits or something like that. Or all pressure vessels exhibit leak before burst design or something. You know what I mean? So we're gonna develop what the testable requirements are for our system first. And then we're gonna create a project delivery schedule, and we're gonna get to work. So right now, over the past couple of weeks, we've been developing a physics model in Python to size the engine up essentially and use some flow equations. And then we're just gonna figure out essentially the way the project management, I think Jürgen can talk more about how the project management is gonna look like week to week. But the general schedule is the first hot fire milestone is June 1st. So we have 18 weeks.
Is that for like a full model, I'm guessing?
Yes. But as far as the club progressment goes, the first engine that we're making is going to be very small. The way I have it sized up right now, it makes like 200 newtons of thrust. It runs at 8 atmospheres of chamber pressure. It's really low pressure engine, low thrust, to make sure that our model is accurate and that we can run this just to develop the controls and the electronics and have everything good. That's going to be our first engine. It's like a learning and development platform. And then the second engine we're going to build probably next semester is going to be a 10 kilonewton engine, and that's going to be pretty cool. So that's going to be the real performance one. But that's the timeline.
Do we have a budget?
Sorry?
Do we have a budget?
So the budget hasn't been, so we don't even have a bill of materials yet, right? So we don't know. As far as the fundraising goes, we're gonna seek for sponsorships and outside money. I'm contributing some portion of my own money. We'll see how that turns out once we know more about. Rather, we're gonna do fundraising efforts now, and then we're gonna see what our bill of materials looks like as we continue.
Yeah, I don't know if the school is gonna like give us money or how much money they'll give us, any. So I'm gonna be going around to different like firms, companies, trying to pitch. I mean, instead of going for like a fuck ton of money from like one company, I'm just gonna try and get like a little bit from like a bunch of companies. And I think like it'll help. Like, I'm gonna contribute some money too, obviously. But in terms of fundraising, like I think we should be fine because Makar and I know a lot of people. And we know, like I mean that it's like we know people that have run clubs, that have tried to do things like this before, and that we can kind of learn from in terms of like fundraising, who to contact, how to do it. So that's but like he said, we don't really have a bond yet, so we don't really know how much money we should be shooting for. So once we figure that out, then we can give you like a better answer.
Yeah. But the day-to-day operations are going to be more like, I want everyone to work as much as they want, essentially. I don't want to be hunting people down and be like, hey, you're not doing this thing that you're responsible for because, I don't know, everyone's a student. If this is something that interests you, this is something that you're going to dedicate time to. And if this is something, if your interest wanes or something happens, you don't want to do it, whatever. It's just kind of a place for us to work on rocket engines. But as far as the week to week kind of operations is going to be, we're going to have a rough weekly outline of what systems need to be completed by when, what kind of tests need to be run by when, and then at the beginning of each week we'll say this we're focusing on this week. We're getting this system out of the door. We're doing these tests on this component. This is, and then people choose what they work on. I want everyone to have kind of experience the breadth of the entire engineering exercise, and then specialize in something that you want to specialize in. It's not like you're on the controls team or on the nozzle team or something, but you get to specialize in the nozzle if that's what interests you, or you get to specialize in the controls if that's what interests you, and we go from there.
And obviously, you guys aren't constrained to like one system. If you guys want to do like a couple things, the more the merrier, also, because it'll help us out. In terms of project management, like you said, we don't want to like give you guys an assignment or something like that and have to track you down. We know you guys are busy. You guys have jobs. You guys have school to go on. But we'll be trying to do our best to communicate to you guys what we need or what we would like from you guys by when. I'm in the Space and Satellites Club at Davis, and the way they run their club is really well structured. Almost like week by week, they give you kind of like the manufacturing team will be doing this, the optimization team is doing this, systems team is doing this, like so on and so forth. And it gives you kind of like every week you kind of know what you need to do. And they don't put a lot of pressure. Like, we know if you guys have something coming up, just let us know so we can take care of it for you, or we can have someone else take care of it for you if they have more time.
But we want to make sure that everyone has there's not like, well, like everybody has something to do if they want to be doing something. Like if there's more people, if we figure out that there's more people than like is needed for the work that we're doing, we'll expand the scope of the work. It's an engineering exercise primarily for the members, so for you guys to do something and to learn something from it. So that's kind of my mentality going into that. I think, anything else?
No, I think that's basically it.
Yeah.
Do you guys have
On
any
time?
questions or anything like that? Yes.
Yeah.
How much time did it take you to research all this about the project?
Gotcha. So I'm a bit of a nerd. So the rockets have been a personal passion for me for a while, and I've been kind of accumulating knowledge over time. I learned a lot of because I decided to pursue this project seriously, basically over winter break, I dove into some more of the in-depth physics, and I learned how to model the gas flows actually inside of the rocket engine, and I created essentially sizing models.
Really?
So that was kind of just, yeah. Well, it's one-dimensional. It's one-dimensional, and it uses the Mach area relation kind of it's not a full and complete picture. It's something that we have to work on over time, but it's something that I've been accumulating over time. Yeah. But
Because we get to like learn that too, so.
yes. So okay. On that point,
How much time?
there's I hope that I can convey what I have learned so far as concisely and as effectively as I can. I believe that you guys, I don't think I should take everyone too long, but it's like you learn, the best way to learn, in my opinion, is when you're actually trying to achieve something. You have a goal, right? You have a project. You're trying to make this thing, and you don't know something about it, so you go and find out, or you talk to people that know, or you go to professors, that's kind of the learning process, I guess. But I'm gonna hold a crash course about, like, in-depth about every single system in kind of more considerations, because I kind of glossed over everything, but there's like considerations that go into the design of each of the subsystems. Yeah. What's up?
Wait, so you said that you have a model in a way in Python?
Mm-hmm. Yes.
I guess, is it like G code or something?
So the model, okay, it's not like a CAD model, it's a model like physics model, right?
Right.
So essentially it's just a spreadsheet. Well, we ported it to Python so we can have a class that holds chemistry values. There's an online calculator that NASA has called NASA CEA combustion something. It calculates the combustion properties of the gases that are created by the rocket, and that's the really difficult part to do. Because, and we'll talk about this more later, but you have a bunch of these intermittent species that exist, and then you have reaction rates you have to consider, and then you have incomplete combustion as you go down, and like you have to figure out how much gas you're putting, how much oxidizer you're putting in versus how much fuel, because it might not be the most efficient way to put them in 1-to-1 ratio because you're trying to maximize different things. So that was that. We got the combustion chemistry data from NASA, and then we did one-dimensional flow relations to figure out the throat size and the nozzle exit size, and then using mass flow rate you can figure out what the thrust is, and then you figure out what the efficiency of the rocket engine is from the combustion chemistry. That's what governs it.
So you said you wrote the physics equations for like the gas trying to come out of the rocket?
Yeah.
The rocket trying to hold it?
Yes.
Can I see them?
Yeah.
Have you set up your GitHub yet?
Yeah, we have a GitHub.
Okay.
We have a GitHub organization. Yeah, we'll talk more about the model and like what goes into it. I'm personally like on the Dunning-Kruger curve. I'm in like over Idiot Valley, and now I'm in the Valley of Despair. So I'm like down here. I'm like, oh shit, look at all these things that I have left to learn. So I understand the model that we made has limitations and things that we have to expand upon. There's a lot of like really weird gas stuff that we have to model. But it's a good general sizing guide so that we have our design points so we can start making the thing over time. So yeah.
We also have, like I said, we have a resources tab for you guys, and there's a couple lectures online from USC and from MIT that do a really, really good job of explaining these things in ways that you can understand. So we have those in like a resources drive that, again, we'll share with you guys, so it'll help. It's not gonna be that bad as long as you guys like actually sit down and like take some time out of your day to do this, because no one's gonna force you to learn this stuff. If you really want to, you're gonna do it. And there are no courses here at school that teach anything like this. But we'll provide you with everything. And if there's something missing that we don't have on the resources tab, feel free to add it for other people that have the same questions or want to know this stuff.
Yeah.
So I think that's basically it.
Yeah.
Are we gonna be meeting every Friday like this, or are we gonna do like every week we see when we're available?
Mhm.
Oh,
Well, I think I don't know about the general meetings, but you're basically going to be meeting with the people that you're working with. So like, let's decide that you decided that you want to work on the nozzle, for example. Okay, cool. You're gonna be in a chat with the nozzle people, and then you can either voice call or you can meet somewhere on campus, or I don't know about general meetings. It's like not everyone can meet at this time. It's kind of hard. I want to extend the capability of like video conferencing and that kind of stuff so that we can have effective communication without having required meeting times.
I think we're also gonna do like a when to meet, so we can have an idea of people's schedules.
Well, we already did that though for the weeks.
Like 5. Oh yeah, we did. I guess we did.
Like 22 responses.
Yeah, I totally forgot about that.
Yeah.
But yeah, I so like for this, once you get into your systems, and once you guys figure out what you want to do, then you guys can get together and figure out what the best time and best way to get together is for you guys. If it's video conference, if it's meeting up at school or something like that, and we'll figure it out.
So yeah, I've just thrown a bunch of stuff at you. Like, look at this rocket thing. But unfortunately, we don't really have anything to work on right now. Over this week, we're going to be working on the design requirements and running them by faculty advisors. And essentially, what I ask of you right now is kind of just, I'm gonna send out this link, kind of think about this, think about what you want out of it, and just click links, try to absorb a little bit of information over time, and then we will do in-depth concept reviews of what the individual systems have to do, and then I foresee design starting week, so not Monday, but next month.
Should we get like everyone's information for like a Slack or something? How do you want?
I have everyone's emails, so it's fine.
Yeah,
We'll send it out.
People have like each other's emails and stuff like that.
I didn't send it as blind, so everyone can see each other's emails. Yeah, we can. If you guys actually, do you guys want a Slack for this or? Yeah, we'll make a Slack.
All right. I guess before you guys leave, just give us your email.
I have the emails, bro.
Oh yeah. It's late.
Don't worry. Yeah. So yeah, let's chill, hang out, and talk, and then yeah. What's up?
I was gonna say, should it be better to have the CSU's email?
I have everyone's CSUS emails. That's how I sent you the emails.
Well, he sent it to me. That's
Oh, okay.
But yeah.
Okay, well then I can get yours. Yeah, what's up?
Are you guys like officially registered or like affiliated with Saxon? Because I know you said you're pulling kids from UC Davis and stuff
Yeah.
too.
So we're not yet an organization. We're working with Seoul to become one, and then because we're looking for like an advisor. It's going to be one of the ME people, one of the ME professors. But we're going to become an official organization. But I do want people. For example, we have Daruv, and then we have Joseph from UC Davis. So I want other people to be able to join the org.
And then part of that question, as far as like resources go for like manufacturing and other stuff,
Yeah.
can we use like UC Davis stuff or like both schools or something?
So I don't know about the UC Davis stuff. They have really nice machines.
Yeah,
I have
I'm
to say.
thinking
Like,
they got some pretty cool stuff.
Yeah.
Yeah, we might be able to take.
We might be okay with the machines that we have here because we have a CNC lathe, which is like really cool. It's gonna be. I think that'll enable us to manufacture the nozzle. But that is something that I don't know the answer to, and if we can figure out a way to do this, then that'd be good.
Cool.
Yeah, I agree. Yeah.
what would you like for us to like, or for like all of us to know what groups we want to be in?
So like I said before, I don't want you to be in a group per se, but like your specialization.
Yeah.
Well, just kind of think about it for now, and I'm going to talk. Let's say after we do the in-depth dives into the subsystems, because that'll give you more of a taste of like what it is. Yeah.
Okay.
Yeah. I don't want to like assign like, oh hey, you're doing congratulations, you're programming. Yeah.
So nothing's gonna be announced till next Monday, you said?
Well, I'm gonna send stuff. I think. Yeah, probably. I don't know. We'll probably meet. Do you guys? Well, okay. We're gonna develop the design requirements, and then the week after next is when we'll start the development. So that's, in that period of time, we'll be setting up the Slack and figuring out what we want our file management systems to be, that kind of stuff. And then I think that's how we'll do it.
Okay, cool.
Awesome. Thank you everyone for coming.
Yeah, thank you
Let's
guys
hang
for
out
coming.
and talk if you guys want, or you can leave.